Okay, moving on to question 2 of your kinetics tutorial. In question 2, we are supposed to plot a concentration time graph of H2O2 at various time. Alright, and using the grid provided, plot the graph. Okay, and we use the graph to determine the order of reaction with respect to H2O2 and the initial rate. Okay, so basically, if you take a look at the context of this question, H2O2 is used as a reactant. So which means we are doing a reactant versus time graph. Right, reactant concentration versus time graph. Okay, so in this case, let's take a look at your concepts. So you recall in your summary of your kinetics, we say that if you plot concentration of reactant A against time, we can have 3 different graphs. For 0 order, right, you will get a straight line linear decay in which your concentrations of your H2O2 or A will decrease linearly with time. Okay, so if it's a first order, that's where we have what we call a constant half-life. So it's a curve, it's an exponential decay, but we have a constant half-life. So recall what's the definition of half-life? Half-life is the time taken for the initial concentration. So in this case, example, I start from time t equals 0, 100% to drop to 50%. This will tell me the half-life. Okay, and then the next half-life will be from 100 to 50. Next half-life will be 50 to 25%. That's what the A over 2 and A over 4 means. That's the second half-life. And if T1 is equal to T2, then this is what we consider as half-life is constant, and therefore it's going to be first order. Okay, and then of course, if the half-life is not constant, it's likely to be a second order reaction. Alright, but that's not a confirmatory test. What we can just confirm is that if we have a graph that is that has a non-constant half-life, it's not going to be first order. Okay, so we're going to plot the graph. Okay, so I trust that you guys have plotted a graph. This is the graph you get, and we're supposed to use the graph to determine the order of reaction with respect to H2O2. So if you take a look at this, is A against time, is H2O against time. All we need to do is to find what's the half-life, and if the half-life is constant. Alright, so again, when you're graph plotting, take note, you're supposed to plot a graph, label your axis. So this is to reinforce what you learned from practical. Label your axis with units. So H2O2 mole per dm cube, time in seconds. That's what's given to you. Time in second, H2O2 in mole per dm cube. Okay, so we plot the points, label the points correctly, and you're supposed to choose a scale that allows for covering at least half the graph paper. Okay, so you can see my graph typically covers more than half of the grid given. Okay, so assuming I plotted a graph correctly, okay, now we are supposed to find half-life. So we start off with this particular value, 0.0200. This is your time t equals 0, 100%. Alright, we are looking at the time taken for it to fall to 50%. So 50% will be at 0.0100. So we first draw the construction lines. So first set of construction lines shown over here. So this is the construction line. Time taken will be this time from time t equals 0 all the way to around 320 seconds. Right, so time taken from it to drop from here is will be from this time all the way to this time, right? So 320 seconds. Okay, that's the first half-life. The second half-life will be from 50%. If you drop another by half, right? So how do I get 50%? It's 100% times half, 50%. 50%, and now half of it will be 25%. 25% will correspond to 0.05. Again, this 25% is of the original 100%. So we're looking at the time taken for 50% to drop to 25%. Which from this point here where my cursor is, time taken for this point to drop to this point, which means the time taken from here, alright, to here. So again, I'm drawing my construction lines again, the second set of construction lines. So you can clearly see now the time taken is from this particular point to this particular point. What's the time taken? From here to here. So it's from 320 to 640. Again, the time taken is also another 320 seconds. Okay, so this is your working here. You need to show, in order for us to show there's constant half-life, what we need to show? We need to have 2 sets of construction lines. Okay, so you can see set number 1, set number 2. Okay, and then we need to label our half-life. So set number 1 half-life, half-life 1, half-life 2. 2 T half, that's labeled. Okay? So construction lines in highlighted in purple, the half-life labeled. Alright, that will indicate our working for the graph. And then since the half-life is constant, I can therefore conclude that it's going to be first order with respect to H2O2. So H2O2 graph has a constant half-life. State the value. So constant, like important points, constant half-life. What's the value? The order of reaction with respect to H2O2 is 1. So this is typically 2-mark response. The deduction is worth 1 mark. The working on the graph is worth another mark. Okay? So this is for part 1, reduce the order of reaction with respect to H2O2. We will now move on to the second part of the question where we're supposed to look at the initial rate. So recall what initial rate is. Initial rate means rate, right? At time t equals to 0. Okay, so how do I find the rates of a reaction at time t equals 0? So recall what is rate. We have a concentration time graph. So remember, rate is always about a change in concentration per unit time. So how do I find change in concentration? I therefore need to find the gradient of this graph. Okay, I need to find the gradient of this graph. But since I need to find at initial rate, I need to therefore draw a tangent of the graph at time t equals to 0. Okay, so importantly for you to realize, I need to draw a tangent, the curve, at t equals 0. Okay, a trick to help you find the gradient easily is to extrapolate a tangent all the way to the x-axis. So that you can just read off the coordinate, you can actually find the difference in the y, change in y over change in x without using the gradient. Okay, so that's what I'm doing over here. So from the graph, initial will be gradient of a tangent at time t equals 0. So notice over here, the next concept I need to highlight to you is the modular sign. Why do I need a modular sign? Because you can see that the tangent from the graph is actually negative. But it's not logical to say that the rate is negative. Alright, so although the gradient is negative, we therefore put a modular sign to convert the gradient to a positive value to reflect rate more accurately. So over here you can see what I'm doing over here. I'm just basically taking the vertical distance 0.02 over the intersection of the x-axis, which is around 470. And with that I can get the rate of the reaction. So remember I said rate was a change in concentration per unit time. In this case the per unit time is in second, it says per second. Alright, so rate is always positive, take the value of the gradient of the tangent. So you show your modular sign, and of course importantly over here highlighted here, you need to show clear construction lines including the tangent at t equals 0. So that's what I'm doing over here. Alright, this tangent, the red line that I've drawn. Alright, okay, so that's the first part. We move on to part B. For part B, we have something similar to what we have done in question 1, in which we have a discontinuous method in which we do multiple runs of the experiments and see how the change in your reactance concentration affects the rate. Okay, so over here there's one part I mentioned here. Each solution is made up to same total volume with water when necessary. So the question is, why is this necessary? This you have encountered in your practical. Alright, so the total volume, if you take a look at this reaction, 10, 20, 10, we keep it at 40, 5, 20, 15, 40, 30, 10, 0, 40. The total volume of reaction mixture is always kept constant at 40 with how? Through adding different volumes of water. So why is water added, different volumes of water added? To keep total volume constant so that your volume of reactant used, right, is directly proportional to the reactant's concentration in the reactant mixture. Right, so this is important consideration that we have for practical. Alright, we need to ensure that we add the corresponding volume of water to keep total volume constant. Okay, so once we have that, we can then deduce the order of reaction with respect to S2A2 minus, given that order of reaction with respect to I minus is 1. So what we need to find is for S2082 minus. So if you take a closer look at S2082 minus, which is the experiment we will compare, we will definitely have to involve experiment 3. Am I right? Because experiment 3 is the only experiment which S2082 minus changes. So we can compare it with either experiment 1 or 2. Alright. So in this case, I decided to compare between experiment 1 and 3. So because both factors changes at the same time, what I've done is to use the calculation method. Okay, so comparing between experiment 1 and 3, again, over here, step 1 first, I write out my generic rate equation. Right, since they say that order of reaction with respect to I minus 1, I have written in 1 here instead of x and y. So once I compare experiment 1 and 3, so I sub in all the values of 1 and 3. So over here, notice that I did not sub in the concentration. What I have done is to substitute in the volume instead. Why can I do that? So earlier I mentioned that we can do this because we came to this conclusion by keeping total volume constant. The volume of reactant used will be directly proportional to the reactant concentration in the reaction mixture. And therefore, I can, instead of substituting the concentration terms, I can substitute the volume term. Alright, so once I have that, sub in the rate values, solve for the question. So your K and K can cancel out. 10 and 30, you can cancel away the terms. So you end up with x to be quite close to 1, and therefore x to be 1. Okay, there are some mathematical steps missing in between over here. So let me show you the mathematical derivation. So from here, you end up with 0.0200 over 0.0303 equals to 1/3 2 to the power of x. So if you work out the math, you have 2 to the power of x equals to 0.6600, alright, over 1/3. And once you solve for this, you get 2 to the power of x equals to 1.980. Alright? Okay? And from there, when you take log on both sides, log 2, x log 2 will be equals to log 1.980, and therefore x will be equals to log 1.980 over log 2, and therefore you get a value that's very close to 1, but not exactly 1, but you will know that we have to round off to the nearest whole number. Okay, with that, we are done with question 2.